and from him you can get this thing on request. There is no issue. Okay, so let's move ahead. Now you see this seismic hazard evaluation that I'm going to uh, sort of teach you, not exhaustively because it is not possible, but I will give you all the important parts, so that later on if you revisit all these things from any book, you can get a very good idea about how to proceed. So if you see that there are three components. The first one is the magnitude recurrence relationship. Second is the ground motion intensity in given time interval. Third is ground motion intensity at given site. That is actually what we get from the attenuation laws. And once you have these three things ready, then we are in a position to go ahead with the probabilistic seismic hazard evaluation. Okay, so let us see what is magnitude recurrence relationship. Okay. Um, I think a few of you must have heard, those who have taken some introductory course on earthquake engineering, that there are few magnitude recurrence laws available, and the most commonly used ones are actually due to Gutenberg and Richter. So there is one Gutenberg Richter recurrence law, and there is one bounded version of that. Okay, so I will discuss what we understand by Gutenberg Richter law and what is the bounded version of that. Okay, now let us see first, I mean, what do we understand by this Gutenberg Richter law? So if you see the equation 1, that is very simple equation. So here you see that lambda m, that is reserved for the average number of earthquakes that exceed a given magnitude m. I think you know what is earthquake magnitude. If you're not very much familiar with this thing, for the time being, you just assume, or not assume, you just remember that magnitude is a quantity through which we measure the size of an earthquake. Okay, so it is the size of the earthquake. Okay, nothing more than that. And there are various definitions of magnitude. So for the time being, we are not going into details of that. Whichever definition you follow, given that particular magnitude definition, there is a law stated by equation 1. So it says that the average number of earthquake that exceeds a magnitude m is actually having a linear kind of behavior when you take the logarithmic of that particular number. So logarithmic of your lambda m, this log means log to the base 10, it is a minus bm. So that means it's a constant is there, and it is decreasing with increasing m. So with m. So it is quite common sense that if your magnitude is very large, that means you are talking about a very large earth size of earthquake, then of course that number will be reduced. You cannot actually experience too many frequent large earthquakes, right? And that number actually reduces exponentially. That is the reason when you take log, you are getting a linear decay. And you can express this thing in terms of natural log as well, ln. And if you do that, then that the coefficients a and b are respectively known as alpha and beta. And the constant that you are seeing 2.303, whatever it is obvious, it is basically log 10 to the base e. Okay, so now you see what is a and b values. A and b values are very kind of textbook kind of things. We always say what is the ab value of that region. So we then really understand that what is the a value and b value of a GR relationship. Okay, so region wise constants obtained from complete catalog data. So that complete I emphasize, because unless until your catalog data is complete, you cannot actually get the right estimate for your a and b. Okay, so now what is the physical interpretation of these constants? You see that a talks about the overall activity rate. Okay, so if a seismic a region is seismically very much active, then of course you are expecting some higher value of a. And b talks about the distribution over magnitude rate. So how the activity is distributed over various ranges of magnitude, that is governed by the b. So you can see that if b is high, that means smaller magnitude earthquakes are much higher in number compared to larger magnitudes for another region for which b is small. Okay, so it is like that. So if you plot your this GR relationship, you will typically get this kind of straight line. These are idealized cases. So if you get a least square feet, you will find you will get a straight line like this. So for one region you have A1 and B1, for another region you have A2 and B2. Now for all practical purpose, we usually set a minimum threshold because we are engineers. We are not very much interested in magnitudes being too small. So for all practical purpose, sometimes we don't consider magnitude less than 4, because if any earthquake comes having magnitude less than 4, its tremor will not be felt even though it is happening quite close to the site. Okay. So then we are actually not, considering some magnitudes less than, I mean some minimum number of size of event that we consider, and that is noted by M0. Similarly, depending on the region, some region may not be able to produce at all, okay, magnitude having size greater than something. So then in some sense we will find that these straight lines, whatever we are actually getting out of GR relationship, they have a some kind of physical or physical bound. Okay. So when we are going to use that, then we call it bounded. I will come to that point later. So for the time being, let us see that what is the typical A and B values to get some idea. So for that, there is a table. It is taken from the source. It is written below. Now you see for various regions, country-wise, you can see the values of A and B. Okay, so you can get some idea about what are the typical ranges for A and V value that you will get if you want to carry out this regression analysis to get your A and B from the complete catalog data. Okay. Now here I just want to say one thing. It is that what is region, for example. We have said Japan is one region, but that may not be the case. Somebody can increase the resolution, right? So a country can be divided into various zones, even like we have in India, right? And different zones will have different A and B values, and there is no end of this resolution. Even within northeast India, we can further find out multiple zones, and different zones will again have A and B value. So depending on what resolutions you are looking for, you can actually subdivide various zones. So if we are dividing this thing into smaller zones, then we sometimes call it microzonation, or sometimes we can do this thing for fairly small resolution. So some cross kind of thing, what is shown in this figure. Every country has its one A and B values. So this is how we usually proceed. So the second thing that I'm talking about, this is the bounded Gutenberg-Richter law. So there we have usually we hear clear-cut mention that look, my magnitude will be greater than equal to something, and it will be less than equal to something. In that case, what will happen? That you see this graph where it is the lambda m plotted in log scale. So you will get the same behavior if you plot directly the log of the lambda. So you see that straight lines, instead of abruptly dropping down at the respective threshold values, you are having some smooth transition. That all happens because of this equation stated in equation number 3. Okay, and it depends on the lambda m0, which is the corresponding Gutenberg Richter lambda m value for the minimum your magnitude. Okay, so this is the one that most of the time we consider because we want to work within a feasible bound of the magnitudes. So otherwise your Gutenberg Richter relationship is open ended. There is no minimum magnitude, there is no maximum magnitude. Okay, so now, as I said, that when you are going to use finally carry out the probabilistic hazard, we need to have various components. So now we have here a very important component, which is the probability distribution of the magnitude. That means here we are saying, now remember one thing, there is no a rate as such. Here we are trying to say that if you, that is the question here, that what is the probability that any randomly chosen earthquake, so you just choose one earthquake, what is the probability that what is the probability that this chosen randomly one earthquake will have a magnitude between m1 and m2. So for that we need to have the density function, the how your magnitude is distributed, and that you are getting from the GR law itself. Okay, so it is basically the first line. If you see, this is nothing but what is the cumulative probability distribution, and once you are differentiating this is the very basic principle of probability, then you are getting the density function for the magnitude. So that is one important thing that we need to always remember, because this is what we are going to use. And as I have said, that beta or b, b is only when you are taking the logarithmic with 10, and beta is when you are taking the natural log. So this is the parameter that talks about the distribution over the magnitude. So you see that A is not coming very into the picture, right? Nowhere it is in the picture. It is only the B or beta value that will fully govern the distribution of the magnitude. Okay. So now we will move to the one of the very important applications of GR relationship that goes in tandem with our Poisson probabilistic model. So here we need to define, or we need to here actually define that how we are going to assign some probability structure, okay, for the number of events. So Poisson probabilistic model is found to be most suitable for most of the cases. It is not that it is the only thing, but it is widely accepted because of simplicity and also because of some physical nature of the earthquake process itself. So here what we understand by event means any earthquake of magnitude greater than m, that we call an event. And then it says that the number of events in a time interval t be equal to x. So given a time interval, let's say you are talking about 50 years. So, and if I ask you that what is the probability that within 50 years, okay, there will be just 20 number of earthquakes having magnitude greater than m. So that answer you will get from equation 7. So it says that the probability that your number of event will be exactly equal to x in a time duration of small t. Okay, that is given by this equation. This is nothing but the Poisson distribution model. So here this lambda, what is that lambda? Because you have defined the event which is the earthquake of magnitude greater than m. So is it not the same lambda m then that you are actually getting from the G relationship? The answer is yes. So that means if you are really going to fit a Poisson model, the very basic input that what will be the lambda, it is actually the lambda m which you are getting from the G relationship. So now if you see here that the main two things that I want to highlight here, that this lambda or lambda m for that magnitude m, it is called the average number of occurrences of the event per unit time. So in generally it are, these are in terms of years or mean occurrence rate from GR relationship, you get it. And 1 by lambda we denote by T of R, and the TR, that is basically the mean return period, okay, in days, months or years. So unless until the earthquakes are too frequent, that is they are very small, you will not find these numbers in terms of days or months, usually in terms of years. So this is the mean return period 1 by lambda at which the event is repeated. Okay. So now unless until we get a problem, so solve a problem, our understanding will not get reinforced. So let us see one simple problem here. So the problem says, there is a statement, it says that if every 20 years, okay, in a time interval of 100 years, the number of earthquakes of a magnitude greater than 7 is as per the given table. So if you see the table, you will find that in 20 years of block, there are just counting the number of events. Events here means any event having magnitude greater than 7. Okay. So now then the question asked is that you find the mean or average return period for that. So it is obvious that we need to fit the Gutenberg Victor, this thing, and then how do you use this one here? So it is talking about the same lambda, you see. So in this case, the occurrence rate of earthquakes with a magnitude greater than 7 for the first, second, third, and fourth. So for every block, you count them. And if you see the previous slide, what is written here? Average number. It is very important, right? So it is an average number. So you already got some numbers for different blocks. So you need to now average them. So in the first block you have 1, in the second block you don't have any. For the third block you have 2, for the fourth block you have 1, and again for fifth you have nothing. So if you get this lambda, you are getting some number. Now what is the unit? These are all in years. So you are getting this thing 0.04 events per year, right? So then you are getting your lambda. Now how do you get your return period? Now if you see this previous slide, it is given that 1 by lambda is the mean return period. That is very important, mean return period, because return period is also a random variable. Okay, that means it is not a fixed thing. You cannot say that one earthquake of this magnitude will come for sure repetitively up to 100 years. every no, certain year. That is not possible. It is only the mean return period. So the mean value of return period is 25 years. So that means it is expected that in every 25th year, an earthquake having magnitude more than 7 will occur in that particular region. I think this is clear, right? This is a very simple thing to start with. Okay. Now, what I'm going to discuss now, it is the ground motion intensity in given time interval. Now, whatever you have, learned or understood by now, is that how frequent or what is the interval of a particular magnitude of earthquakes. Now, if you slightly think, okay, quietly, then you may understand or you may ask me that why I will be interested in the magnitude. Because I said in the very beginning that magnitude is the size of the event. Now, for the time being, forget about earthquake. You just think that whenever I'm talking about earthquake, you are thinking about some kind of explosion. Now, whenever some explosion happens, you will get adversely affected. Now, is it really dependent only on the size of the explosion, or whether you are close to it or far away from it? That is all that matters. A very large explosion might have happened, half a globe away from you, which will have no effect on you. And you have a small explosive things, maybe a small cracker bursting in your hand may cause you a lot of damage. So it is not only the magnitude, rather how much intensity of the motion felt in that particular site of your interest. That is the main thing that we should be concerned about. If there is a magnitude of earthquake of 7 or 8, quite large, but occurring in Japan, will have no effect on a structure which is there in India. Okay, so we are now interested in to estimate or to understand first at least that what is the intensity. Now, intensity is a very different quantity from the magnitude itself. So this is the actually the real tremor that you feel at a site. So there are various parameters which are of course the ground motion parameters. So earlier the parameters that we dealt with, these are all with respect to the catalog data. That means the year when the earthquake happened, what is the size of that event happened, where it has happened, all these things. But none of them will tell you that what is the intensity of the shaking, that how strong shaking actually is there in a particular site. So there are certain measures. These are sometimes called the intensity measures or denoted by IM. I use everybody's IM, the intensity measure. So these are parameters like peak ground acceleration or pseudospectral acceleration or pseudospectral velocity, spectral acceleration. That is either the response spectral quantities or some of the quantities of the direct ground motion itself. That is the peak ground acceleration. That is the maximum acceleration recorded in a particular ground motion in absolute sense. Okay, plus minus whatever it is the magnitude of that. So those who don't know about this, the response spectral quantities. For the time being, you just assume that they are all collectively characterizing the ground motion itself. Okay, stronger the ground motion, all these three values will be higher. So intensity measure is something. There is also a random quantity because we don't know that what will be exactly this value. So we here also we want to assign the occurrence of this intensity measure into the same Poisson model, because that is something which is important. Whether a magnitude of earthquake is coming every year greater than certain things is not that much important for an engineer as what a particular amount of tremor being felt periodically is important. So what we are going to do here, that we will try to formulate a kind of similar framework, very similar framework that we have just framed for the magnitude. So what we will do in that case, let us make two statements. Statement one, an event occurs with magnitude greater than m. And statement two, the intensity measure, capital Y is the intensity measure which is random, but it will specify, it will greater than a specified value small y. Okay, it is denotation is like this. Small y means it is a specified value, and capital a variable means it is that random variable which can take any value. So intensity measure when y greater than the small y at a site. Now the assumption is that statement 1 and statement 2 are equivalent. That means always there exists some magnitude m, that whenever there will be earthquake having magnitude greater than m will also produce intensity measure greater than small y, and that is very much acceptable provided other affecting factors of the intensity measures are not changing. So again, you think of that explosion that I talked about earlier. Let's say there are several factors of the traveling, the kind of sound that you will hear, because it will travel through air or some medium. Okay, let's say all factors are constant. Then you can always say that if you want to get a noise or a sound more than certain level, then you need to have an explosion of size bigger than something. So that means having an earthquake greater than a particular magnitude is equivalent to say that having the intensity measure also greater than that. So then we can use this equation 9 directly to get this intensity measure into a Poisson model. So then we can say really that if xt is the number of occurrences of such an event in a time interval t, then the probability that the ground motion intensity at the site will exceed a certain value is simply, the first term is simply, what is the probability that that particular event exceeding m is greater than equal to 1. That means at least one event will occur. Now what is the probability of at least one event? It is actually complementary to no event will occur. So 1 minus probability that no event will occur is actually at least one will occur. So it is 1 minus e to the power minus lambda t. So this value you will get directly if you put x equal to 0 in your Poisson equation here. Where is that? Here, if you put your x equal to 0, we will eventually get this thing. So it is very simple from there. So now at least we connected. How? What we connected? We connected the occurrence model of the earthquake with the occurrence model of by intensity measure crossing certain values. That is very important for us, right? As an engineer, we want what is the shaking. We don't care for what is the magnitude as such. Okay. So now, if you again solve a problem, it will be clear to you. So the problem says that from the analysis of statistical data on the occurrence of earthquakes near a construction site over the past 100 years, it is found that a peak ground acceleration of 0.01 g is exceeded 5 times in those 100 years. Okay. What is the probability that a peak ground acceleration of certain value be exceeded in a time interval of 45 years? Now here you see there are 2 years, okay, duration of years rather I'd say. One is the 100 years. That is the study period. You are studying the background seismicity for 100 years. And this 45 years is something that is have a very, that this is significant for our structure's design life. You have to understand that you are building a structure. The structure is there to stay for a designated period. And you are trying to calculate what is the probability that a particular intensity measure will exceed certain value. Now that exactly that statement, that the probability of exceedance of an intensity measure, exceeding certain values, is what we understand by hazard. So whenever you're talking about hazard, it is essentially a probabilistic quantity, and it is also probability of exceedance, because it is hazardous. We are trying to always imagine that something is going to exceed. Okay, if your ground motion is lower than something, is not hazardous, it is more than that. So what is the probability that a ground motion will exceed a certain value given an exposure period? This 45 years is an important parameter. If you change this thing from 45 to 100, your hazard will increase. It is common sense, because if you're going to stay there for a longer time, of course you are inviting more hazard. Imagine that you are inside a jungle, right? So if you are there for 1 hour and somebody is staying there only for 5 minutes, so it will be more hazardous to the person who is staying there for longer time. So it is just like that. In a seismic scenario, a structure staying for longer time, so it is more hazardous. Anytime anything can come. So this duration is also important. Now you see that everything is actually embedded in this particular formulation. How? Again, through the Poisson model. You see what is happening there? The solution is that like this. So from the given data, what you will get? First, you will get the lambda, because it says that it is found that it is exceeded 5 times. So 5 times this particular level, has been exceeded in 100 years. So you can get this, that the average, per year events is this, which is the occurrence rate, this lambda in your Poisson model, right? Is a per year. Now you say that which is equivalent to a return period of 20 years. Then what is the probability of exceeding that a PGA of this in 45 years? it is 1 minus e to the power minus lambda t. So this is a formula, right? There's a t here. So this is how that time interval, is actually getting into the hazard, which is y exceeding certain values. Now it is clear, if t is increasing, what is happening? A negative power is increasing, right? That means that entire quantity is reducing, and it is 1 minus of that. That means your hazard is increasing. So increment of hazard is common sense, but quantitative estimation is not. So for that you need to use this formula. So it says that it is really quite hazardous. That means in 45 years, chance of being exceeded this particular G.01, quite small, is 0.895. So it is very close to 1. So almost that, I mean, you can say that it is very likely that this thing will get exceeded eventually. Okay. Now I want to say here one thing, that when we do the seismic hazard, okay, so this lambda is a milestone or landmark. What is milestone or a landmark? It is something that you will always trying to find, and after that you are on a home run. So that means when I will give you a problem where you are not getting any clue, your first thing will be to arrive at what is the lambda. Once you know that, immediately then you can get what is the probability of accidents for a certain number of years. That is the design life of the structure. Okay, your structure is going to stay there for certain duration of time. So this is very important. So all your entire seismic hazard will be how to get that. Here we have said here that it is found. That is the key. Nobody is going to tell you so nicely in real life that in 100 years we have found that this much of G is being exceeded 5 times. This statement nobody will give you. So entire seismic hazard, probabilistic seismic hazard, is to actually evaluate or to estimate what is the lambda given your some lower level information about your seismic scenario of that particular place. Okay, then you can get this lambda. Once you know that, it is the same procedure that you are doing here. You need to just fit into the Poisson framework to get your hazard. So now you see that this is what we call a hazard curve. This kind of curve now you can actually easily generate from this thing. So what you are getting, if I tell you any particular G, you can tell me what is the probability of accidents for that, and you treat this thing as a parameter. Let's say you fix 50 years. Now you can get a wide range for this G value. Let's say 0.00001 to maybe even 10G. Forget about whether the 10G can at all happen or not, occur or not. We are not considering that. Let's say any range. For that entire range of this thing, let's say 50 years, you can always pair up that what is the G value and what is the corresponding your probability of accidents. So if you do that, then let's say for 50 years you will get a curve like this. It will say, let's say from here, so anything which is less than, let's say 0.00, let's say almost close to 0 pg, let's say 0.001 pg, let's say anything less than that is having hazard 1. That means what? The 100% certainty that that value will get exceeded in 50 years. Similarly, on the other side, you will see if you take a very large value, anything say more than 0.5 G, you will say that given that particular hazard problem, I mean the seismic data, the probability of accident is almost 0. That means there is no chance that hazard will exceed this 0.5 G for that region for which you got all this thing. Okay. So now similarly you can do this exercise for different years. Now it is also obvious that if you increase the number of years, that is your exposure time, then your hazard for any particular level, let's say 0.2 G, it is increasing, right? So when you have your exposure time longer, you are expecting that chance of that particular value being exceeded will also increase. So your hazard will increase that way. So this kind of curves are called the hazard curve, which gives you hazard from 1 to 0 fully. So once this curve is ready, this is just like a kind of curve that a person can use with, just like a layman. It's very easy. So having that curve generated, now you look at the problem 3. It is very easy. It says that what is the PGA associated with 30% of hazard in 50 years of design life. So you look at the 50 years curve, you find out, okay, probability of accidents is 0.3 because that is 30% accidents. Then you draw a horizontal line, it will cut here, then you come down, you will get a value something around 0.15. So then you can get this number very easily. But now the main focus is that you should know how to get this curve, and for that you need to use this particular equation. Yeah, this one will give you everything. With that particular T, you can actually get this entire hazard curve. Okay. Now, just one thing I want to ask, Vipin. Okay, I mean, is my pace is fine, or I want to be? You want me to be a bit slower or faster? Is it okay? Is it okay? Okay, 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 okay. Thanks. Okay. Now, the next component is the ground motion intensity at given site. Okay. Now, this is again a very important thing. You just try to see, how things are connected. I'm trying to always, focus mostly on that. Now, I think I told you that how GR relationship is connected, because that lambda value you need to input in a Poisson model, right? Now, I also said that Poisson model itself for magnitude is not going to help you, because we want to directly know what is the intensity, the shaking. That is what we are interested. So now we also knew in just the previous section that how to probabilistically estimate even that particular intensity. But the physics is missing. What is the physics? Physics says that if an earthquake occurs somewhere, what is the intensity I'm going to felt? That answer is not yet done. I mean, nobody has given. So unless I get this answer, that the actual physics is not missing, I only have the mathematical models. These are basically just the mathematical things. Is there any physics? No. These are all data crunching. I have given you the data and you are getting the probabilistic estimate. But where is the physics? The physics is that if earthquake is there, what is the shaking? Or in other words, if some explosion is there, if this is the medium, then what is the amount of vibration I will feel? The physics is lying there, right? So then this is actually the physical connection. So this is the ground motion intensity at a given site. So if I ask you a question that, look, there is an earthquake occurred 50 kilometers away from my site in that particular direction. The focal depth of the earthquake is this much. This is the nature of the, the propagation of the, the medium of the wave propagation. I am sitting on a alluvium basin, right? Can you tell me what is the probabilistic estimate, again probabilistic estimate of my peak ground acceleration? Because nobody can tell me in 100% certainty that an earthquake occurs there with magnitude 5, exactly my PGA will be 0.125 G. Nobody can say that. But one can get a distribution of that. That is the, I can get the mean value, the standard deviation, all these things for the PG. But the physics is there because now we are trying to map a physical phenomenon, earthquake, and the exact amount of ground shaking that I'm getting here. So entire physics is involved here. So that is actually addressed by attenuation model. Okay, so that is an integral part of the hazard. So we need to first understand before getting a kind of attenuation relationship. Now it is very difficult to get the actual physics captured in closed form equation because things are highly nonlinear. Some of the subjects are not known. It is very difficult. So what we do, we try to fit some empirical model. Now fitting empirical model also requires some understanding on what are the possible factors that will affect the ground motion intensity at a particular site. Okay, so the most obvious things is of course the magnitude. If all are fixed, one can easily now say that bigger the earthquake, higher the shaking I will get. So of course earthquake magnitude is one thing that is important. The immediate second important thing will find that will come in your mind naturally. That is a distance, right? From the explosion kind of example, you can always relate that how far it is from me, how big the explosion is, and how far it is from me. So same thing with the earthquake. These two are very important. That what is the size of the earthquake and how far it is from me. Okay, now how far it is from me itself is a very big topic. So I'm not going to going into the details of that. This figure taken from this book, so that figure tells you, intuitively, I mean, not intuitively, you can actually really figure it out that what are the various distances. Like this is the first energy release, which is called hypocenter. So from your station, if you get a straight line from here, then this d1, it is the, we call it hypocentral distance. Then just point right above this thing is called the epicenter. Then distance from epicenter is epicentral distance. There is a fault line, is called the nearest distance of the fault projection. Then this is the high stress zone. Accordingly we have distance. This is the region, shortest distance from the, your region of, the rupture zone. So there are a number of distances, but we can say always that higher the distance, smaller will be the city, right? So it is up to you which particular distance you will consider, but you have to consider some distance. Okay, so earthquake magnitude, distance, these two are very important and they will dominate actually the relationship usually. Then you have the focal depth. Of course, your distance, this distance, hypercentral distance, is dependent on the focal depth, but still you can consider focal depth even though you consider hypercentral distance, because there are certain physics which explicitly depends on how deep the event is. So if you want to really capture that effect, you have to consider focal depth again separately. And then you have the dimension of the rupture area, and of course the geological characteristics of the wave propagation of the medium. This thing sometimes very difficult to characterize. If you cannot do, then your entire analysis will become region specific. It is very simple. If something is very specific for that region and I don't want to, in that case, I really don't want to know what is this thing because it is specific to that region only. But if you can capture this effect, then your this thing can be applicable to other region having geological characteristics as one of the parameters. So then you seek your local site properties, that is your the site condition, whether you're sitting on a rock or on a kind of alluvium. Depending on that, things might change. And the type of fault, I mean, it is not every time you will find in models, but if your the faulting, the style of faulting is different, deep slip, strike slip, or there are many other things, oblique slip. Depending on that, also your intensity measure might change. So this is a very typical. I would not say it is the most general, but it is a very typical form of the regression model that we have. That here you have the logarithmic of your intensity measure, and then you have one constant, and then you have one constant with magnitude. You can expect, of course you can say, if I ask you that what is the sign of that c2, I think all of you will say it is plus, because if m increases, of course my intensity measure will increase. This is the logarithmic of the distance term r. It signifies the geometrical spreading. Okay, you know, geometrical spreading means when some energy release and it propagates, it's having a wave front. So energy is, you know, equally distributed in that, you know, spherical surface area, sometimes cylindrical surface area, sometimes very complicated surface area, the way earthquake, you know, wave propagates. But it is some polynomial of the r, with respect to which it is decreases. Okay, like, you know, the inverse square law for, you know, magnetic flux or your gravitational flux. So it is inverse square law wise it is decreasing. So here it is some other polynomial complex kind of thing. It is not very easy. So it is a natural logarithmic of that distance. If you take, then that, you know, effective power will come out as, you know, c3 here. But one thing is sure, that the sign of the c3 will also be negative, because with increasing distance you will have this thing smaller. This y will be less. And this c4 in some sense considers this, you know, the dimension of the rupture area. Your distance can never be zero from all the, you know, sources of your energy release. It is not the only point of energy release, the first point. So energy is getting released from everywhere. So given any point, even though it is sitting on here, the distance is not zero from anywhere. So this thing will never be zero. Mathematical also it will blow up if you get this thing zero. So this is the several other terms. I'm not going into details. So you have some source also as a function of source or function of soil. This linear term takes into account the frictional loss of your energy. So these are many things. So without going into much details, but what I'm trying to say that it captures the physics. That is important. That you have to always remember, that attenuation model captures the physics. So if I give you this much of magnitude, this much of distance, this much of, you know, type of fault, the source mechanism, this is the type of soil, then what is my estimate of the intensity measure? Only this particular model can give you that. Okay, so this is one typical kind of thing that I'm going to show you. It is very famous attenuation model. So you see they have a square term as well, because with magnitude it gets saturated, so it's not linearly increasing. The log of this thing is not linearly increasing with m. So b3 I would expect is negative, and it is negative. So there is a saturation with respect to increasing of magnitude. You see that lnr b5 is all negative, and you see that b2 is all positive, right? So it will increase. So it will capture, of course, the physics, no doubt about this thing. Now here this intensity measure is not the PGA, that is the peak ground acceleration. It is the spectral acceleration. So those who don't know, it is a response depending on the natural time period of the single degree of freedom oscillator. So here all y's will depend on the period. So will be all your coefficients. So coefficients are also, you know, plotted, you know, shown period wise. And this is one very important thing. This is probabilistic. You cannot say for certainty that it is going to work. So there will be error. Error will have distribution. So if you have good number of, you know, data, and if you compute this thing with some maximum likelihood based, you can always get, or it is guaranteed that your error will follow normal distribution, zero mean normal distribution. So if it is zero mean normal distribution, we have only one parameter to define it, that is a sigma. So this is the standard deviation of a zero mean, your process. So it is normal distribution for ln of y. So that is the reason we say that y is log normally distributed. That is equivalent to say that logarithmic of y will follow normal distribution. So this is your sigma, okay, and this is your period. So when period is 0, that is equivalent to the peak ground acceleration. If this is pseudospectral acceleration, for period 0 it is the PGA. So this will also give you the value of your PGA as well. If then in that case you have to take the first row of all the coefficients and you will get the estimate for that. Okay, I think it is clear, right? Okay, fine. So this is just I mean tabulation of the entire thing, so you don't need to focus on that. I will share this thing, you will find. So now let us see one problem to further uh, enhance our understanding on this. So it says that you see that this complete physics is there. You see it says very clearly that find the mean and median plus one standard deviation values of the peak ground the peak horizontal ground acceleration. So it is talking about what is the intensity measure. Read it that way. It asking you to find out the intensity measure given the earthquake properties, only magnitude and distance. You see it says that acceleration at a site that overlies a soil deposit, it says the soil local site condition is located this many kilometers away from, so it know that how far is the earthquake. And he's talking about the fault. Okay, the fault is this much away from your site. It is estimated that earthquake with a moment magnitude up to this may occur in this fault. Similarly, it is estimated that the focal depths of this earthquake will not be greater than this much. The average shear wave velocity for the soil deposit at the same site is assumed to be this. So why they have said all these things? Because these are the parameters for this particular attenuation model that we are going to use. Okay, so what attenuation model we will finally use will depend on what are the parameters and whether they can be accommodated in that particular attenuation model or not. So now you see that you know this thing. So you just simply apply, you get your R, and then you just fit in this model. You need whatever here. Everything is given. NW is the moment magnitude is given. This VS is given. Your R you can compute now, and these coefficients are available from the table, so you directly get this logarithmic of this. Now this value is the average value, because for zero mean standard Gaussian distribution, if you have your sigma associated 0, then the value is basically your median value, or mean or mode. 3 are same for normal distribution, right? For your standard normal distribution. So now the sigma also you can get from the table. So then this is the AH, and then e to the power this plus sigma, if you add, you will get this value for your mean plus sigma, and there is the mean. So you have then what are the things asked? They ask you to compute the mean and the mean plus 1 sigma. So you got the mean and you got the mean plus 1 sigma. Okay, so now in your probabilistic framework you will see that this attenuation model along with this uncertainty defined in terms of sigma, these two are integral part. You will use them in your probabilistic seismic hazard. We are not going to use any particular sigma. We need to know the entire distribution for that. Okay, so that we will see next slides. Okay, in the next slide. So I will take, I mean, maybe 1 or 2 minutes break in the sense that I will speak something but not into this particular topic, because you need to now assimilate a little bit whatever you have seen so far. You just look at your your hand notes if you have written something, and try to now see until this point how things are connected. Try to recapitulate. So how we started with the recurrence law. Then the question comes, why it is important. If it is not there, what would have been the problem? The problem is that now from the recurrence law you got the annual rate of accidents, right? A particular earthquake will occur having magnitude greater than m. Why it is important? It is important because we are interested in the intensity measure, and we know the relation, that is the equivalence of statement 1 and statement 2. I can always say that there is an m for for every earthquake exceeding that m will also cause intensity measure more than a certain value, right? Now we set a Poisson model for the earthquake event. So using this equivalence of the two statement, we can always say that I can also fit a Poisson model for the intensity measure as well. And then given an exposure period, this is very important because every structure will have a design lifetime. So for the design lifetime, I can now tell that what is the probability that a particular intensity measure will be exceeded due to the backdrop seismicity over this period of your design life, right? That is very important. So GR relationship, lambda value, Poisson model, their importance is now understood. So what is left? The physics. Nobody can now tell me before the attenuation model that how do I know what is the intensity measure if some earthquake really happens with this and this magnitude at such and such distance from the site. So that answer we have got. So basically we have now learned a few maths. We have also learned some of the physics. So we are technically now having everything those are needed to finally, reach our target. That is what is the probabilistic seismic hazard evaluation. Okay, so now I'm going into it. So again, the first slide is a kind of, refreshing the all ideas. So you see the number one, what are the things actually we are considering in probabilistic seismic hazard analysis? Number one, uncertainty in magnitude. Now you already know the answer. We have taken care of this thing. How? Because we have got the distribution, that's f, small f of m in previous slides. What is the density function? That is magnitude we considered as a random variable, and we got its random and its probability density function from the b or beta value of your GR relationship. So we have got it already. Second thing is the uncertainty in earthquake location. That is a new thing that I will discuss in this particular section. But we will also consider the uncertainty in the earthquake locations. And what is the third? Now you have learned it already. It is the uncertainty in intensity measure given magnitude and source to site distance. Or sometimes we call this entire thing, that magnitude and source to site distance and many other things, we call sometimes the earthquake scenario. So given a particular earthquake scenario, what is the intensity measure at site in probabilistic sense? That is the distribution of the intensity measure that you can actually get from attenuation relationship, because mean and sigma both are given to you. Okay, you know the mean value of the estimation and you know the sigma of the error, and you know the normal distribution is there after taking log, or y is following log normal distribution, you know that. So the entire uncertainty now is known to you. Entire means 1 and 3. I will tell you how to get this too. Now, some of you might be, thinking that there is another term, what is called deterministic seismic hazard analysis, DSHA. What is that? Now, there is no need to learn this in separately if you learn what is probabilistic, because from the probabilistic framework, if you drop the first two, what you will be left with is essentially the deterministic. So it is only the earthquake scenario is deterministic. That means you already know where it is located exactly. Some judgment is needed, and you also know what is the size of it. So that means uncertainty of earthquake location is not there. Uncertainty in magnitude is not there. So what is there? It is only the uncertainty in the attenuation model. So intensity measure uncertainty is still there. So it is still probabilistic, right? So it looks like no oxymoron because you are saying that is deterministic. Then why it is probabilistic? Because it is because of the hazard. As I said earlier, by definition, hazard itself is probabilistic term, right? What is the probability that a particular intensity measures value will get exceeded during a specified exposure time? So it itself is a probabilistic measure. So this deterministic term is associated with the scenario being deterministic. So in probabilistic, seismic hazard is the most general, where we also consider the location and the size of the events may also be uncertain. Okay, so now as I said that we will see how we get to know the uncertainty in the location. So for simplicity, we assume a line source. It could be area, it could be a volume as well. So just to give you a flavor. So you see that there is a fault, you have a site. So minimum, the maximum to distance will be at the further 2 points. here that left side maximum is smaller than the right side maximum. So, and this is the minimum. So minimum, this thing is here r min. So if you see, if you go through this thing, is very easy. It is saying that what is the probability that r will take some value in between is same as what is the probability that your L will be anywhere between this and this. So from there, very easily you can actually get to know what is the distribution function of this L. So when your this distribution function of your R, when is R is within ml either side, then it is 2 times of this side or that side. Okay, so this is once you will get this relationship, when your R is less than ml, so it is a mirror image of this side of the minimum distance and other side of the minimum distance. So it is 2 times of r min to your R. This is actually your probability that your distance will be less than equal to R. And for the other part that is exceeding some, I mean, you take r ml this way, and then for that extra part you have to add this 1 by of this thing, which is from ml to r, where r is more than rml. So I'm not going to, I mean, go into this annoyingly detailed stuff, but you just think once, it is very clear. Okay, no need to explain this thing here explicitly. So what is important here, we will remember that there is a way to get the distribution. That is, I also know what is the probability that your distance will be within this range to that range. Okay, so you are not, like deterministic case, you are not saying that your earthquake occurred exactly here or exactly here or exactly here. No, you are considering it can occur anywhere, and that probability structure you is actually defined by this density function equation 10. So it will tell you that what is the probability that r can take any value between the entire range from here to here. I mean, undoubtedly you will get the answer 1, because it will be somewhere. Okay, so this is the equation that you will get. So now we are coming to the almost towards the end, that we are now reaching the final products. So here at least you will see that one by one we are actually now getting close to our final listings. So now this is the probability of exceeding specified value of ground motion parameter. Now this is nothing but what you have understood by now from the attenuation law. So attenuation relationship will actually give you this left hand side. You see there is a difference between okay, I will show you later difference between. Okay, I will come here. Now you see, because I want to emphasize this conditionality, it is very important. What attenuation model tells you, now you question yourself, was there any recurrence when we are discussing about the attenuation thing? No, because we are talking about physics. What if? That means the scenario is given already. I told you this is the magnitude, this is the distance. Tell me what is the intensity measure, right? So at least the problem is defined. I have given you magnitude, given you distance, and ask you, tell me what is the hazard, probability of exceedance, certain thing that you can actually get. But that is not the final answer we are looking for. Why? Who will give me the magnitude and distance? I only know the background or the backdrop seismicity. I know the recurrence model of magnitude. I know the possibility of location of the distances, but no one can tell me what is the magnitude, what is the distance. So your attenuation model actually gives you the conditional probability. That means what is the probability that your ground motion intensity will exceed certain specified value given the magnitude and distance. But what we finally want to know, when this given thing is not there, that means I finally want to know that I am sitting in a city. I know the backdrop seismicity defined by Gutenberg relationship. Basically, I have the Poisson model in my hand, and I also know the attenuation model. I want to really know the quantity without this condition. That means, knowing that location, I want to know what is the probability. Tell me what is the probability that my PGA of 0.5 will get exceeded, because that information I know to design my structure. I have to take a PGA value for design of a structure whose exceedance probability is very low, depending on the importance of the structure. But to get that answer, this is the first stage, that what is the probability given what is my magnitude and distance. That answer you will get from your attenuation model. because attenuation model can directly give you this quantity, this ln y you are solving from your attenuation model. You already know the expected value, that is your directly the value you will get in the equation, putting your sigma term 0, and then divided by the sigma you are getting a standard normal distribution, and then it is basically the experience probability 1 minus the confidence, which is minus infinity to z is the standard normal distribution formula, and you are getting everything in terms of z. Now z here inside, what are the things? Z means you will put z here means you are putting y indirectly, which is having inside your m r everything, right? So that you remember in your mind. Okay, so it is the function of z eventually, and z is y, and y means ln y means in your attenuation model ln y depends on your m and depends on your r, that you remember. So equation 14 will give you basically this thing. What is this thing? Given m and r. So now, before wrapping up everything, we want to see the effect of multiple source. I am here sitting in a particular site. I may not have only one potential source of earthquake. There may be more than one faults or seismogenic zones around me where from earthquake anytime can occur and I can feel the wave. So it says very simple thing that if your site of interest has ns numbers of potential seismic sources, so for each particular thing you find out the rate of occurrence causing y greater than y from the ith source. That we will see how to do it, how to get this quantity. Once you know one site, so rate of occurrence you can always sum up. If one source give you this rate of occurrence, another source gives you another rate of occurrence, if you add them up, that means it is the annual rate of occurrence from all contributing sources. Okay, and here I talked about the milestone, right? So now you see you can get the lambda, and you will be very happy the moment you will get lambda, because then directly you will fit in a Poisson model given any exposure period and you can get the hazard. Okay, just like your problem number 2. So if I quickly go to problem number 2, can I, let me see, I think it is problem number 2. Yeah, you see where is, yeah, this is the lambda I'm talking about. If you get this thing somehow, then it is home run for you. Immediately you can solve this thing, right? No problem. So we are really getting close. So now this will tell you how to get this lambda for one particular source. Now this is nothing but this equivalence of statement 1 and statement 2. The probability of exceeding a particular value y of the ground motion parameter, this thing greater than this probability, is same as the relative occurrence frequency of earthquake whose magnitude is larger than the magnitude m that is necessary to produce a level y of the ground motion parameter. That means it is, I'm saying that there is an existence of an earthquake magnitude m. Whenever an earthquake exceeds magnitude m, your intensity exceeds the specified value y. So that means the probability that y greater than y. Here there is no condition. I don't need to. Y greater than y is same as in what proportion you have earthquakes more than that magnitude causing y greater than y, divided by the total number of events. Now total number of events you will get by multiplying any t, so tt will get cancelled out, so it is the ratio of the rate of events having magnitude more than m and rate of all events. That is nothing but the probability from the first principle. Now this equation already you have seen earlier, so you fit it here and then directly you are getting this lambda from your lambda m0, that is the Gutenberg relationships lambda m0 for your minimum value of earthquake multiplied by this thing, probability that y greater than. Now how to get y greater than y, that is now the only thing that we need to find. You think we got everything. Okay, once you know this, evaluate this, you can get this, and knowing this thing means you know everything. That is your main landmark where you have to always go to finally get your solution. Now how to get this from this? This is y greater than y given, and this is truly y greater than y with nothing given. That means I have to consider now the probability structure of m and r. That is the conditional probability, right? This given this thing is conditional. So how to get this thing without the condition? Then you have to consider how m is distributed, how r is distributed. If you use them, then you can get rid of the condition finally and get what is your probability that y will exceed a certain value. That is, it will give you the hazard. So now this is the final expression. So we will do step by step. This equation is the fundamental equation of probability. I think you will find this thing in any probability book. That probability that y will exceed certain value, small y, is same as y exceeding that value given this and this multiplied by all density functions. Density function of m multiplied by density function of r, and then you integrate dm dr double fold. That is this. Now you have already got this. This you have got from your GR relationship earlier, and this I have shown in the figure, that how to get the distribution of your distance anywhere it can happen. So this thing also I have mentioned, where here, you know this. So this adds another one fold of integration with respect to minus infinity to z. So here now you see what you need to do. You put this thing here, and this one you put another integration for z, so it is become a threefold, right? Now for simplicity we assume this thing is 1. This is true when your m max is unbounded or m max is really very large. Then a negative high power of exponential will take it almost to 0, so it will become 1. Otherwise, whatever, this is a constant thing anyway, so that constant you have to account for in the denominator of that. For the time being we didn't do this thing so that it looks neat, and it will serve the actual purpose, no problem. So let's say it is not bounded, there is no m max. M max is very large, so this entered thing will become 0, so it is 1. So fm is simply beta exponential this. So if you do all this thing, finally it will come out all the constant outside, and there are three fourths. So what to do? This is a dummy variable minus infinity to z. So if you, let's say, first integrate with respect to s, then as per the integration law you have to consider other two are constant for the time being. You do the integration, you will get everything in terms of z. Now z there means ln of y. Ln of y means you have m and r already sitting there. So that means the moment you will put that limit here z, your everything will inside will depend on your m and r, and then you do the integration with respect to any one of them. Let's say m, consider r as being constant for the time being, carry out the integration, and then finally do this thing. So you have to do all these definite integrals one after another, and then you finally get the results. Once you will get the results, job not fully done, because I need to get this. So once you will know this, you use the lambda m0, the information will be given to you, and then you directly get your lambda iy. Now the moment you will get that, you will jump to your Poisson equation, fit there 1 minus e to the power minus lambda t. Given exposure will be there t, let's say 100 years or 200 years or 50 years, whatever it is, you directly get the hazards, and that's all. So let's see one problem. Now this is the most comprehensive problem as of now, okay, because earlier was all part basis, but now this is a comprehensive problem where you have to apply all of the knowledge whatever you have gathered. So I mean, read this thing very carefully, okay? So and try to understand what it provides. It provides very low level information. That means the kind of information that is very easier to get, and then from there you can actually estimate now that what is the hazard. The most important thing, that what is the probability that a particular, PGA or any spectral quantity will get exceeded. Or inversely also you can say that if I want to go for probability of exceedance just 1%, because I want my structure to be 99%, kind of safe against hazard, then you have to choose accordingly that particular PGA for that region, which may be quite high. But let's say you will take that thing no matter what. You will consider a PGA whose exceedance probability is not more than 1%. Okay. Another important structure you can go for even 0.1%. It is up to you, whichever value you want to choose. But now you are in a position to get those numbers associated with the hazard or exceedance probability. How to do that? Now you see the site shown in the figure is located in the Western United States and as shown in this figure. So it is a schematic. I have taken this thing from the same book. It's a very good book. You will try to get a copy of this online, or from your library, wherever it is. Very, very, very nice book. You will find everything whatever I have said today. Now you see this, there is a site, so distances are there. These are the fault lengths are also given like this. So you see the site shown in this figure located in the Western states, and as shown in this figure, two active faults are near the site. Okay, so you can see that the two faults are there. Now, the closest distance from the site to the surface projection of fault 1 is 10 kilometer, and to the surface projection of fault 2 is 20 kilometers. So you focus only on the information, not on the values. So basically, they have given you the fault, how far it is from, the geometrical property is given, you know where is your site, and they have also said that the maximum distance are this and this, so you know what is your RML, what is your RMR from the figure, so that you can connect everything accordingly. All informations are given. Now, the estimated fault lengths are this and this, that is also given. And it is also said that from the previous investigation of the area seismicity, it has been determined that the maximum magnitude of the earthquakes expected at fault 1 is this, and the fault 2 is this. So it is obvious that you are going to consider the maximum earthquake to get the the conservative estimate for your, I mean, hazard. Conservative, not the maximum value of the hazard that you can actually get. So you have to consider the, this magnitudes range. Okay, so then similarly it has been determined that A and B constants that define GR law are this and this. So you see they have given AB values. In the previous equation I have shown alpha beta. You know how A, B are related to alpha and beta, right? Alpha is simply log 10 to the base E into A, and beta is log 10 to the base E into B. So that constant is something 2.30. So you know A and B and alpha beta. I mean, you can know what are these values and how to use them. Okay, in your previous equations. So now this is given, and also you see they have given the backdrop seismicity. The backdrop seismicity means basically this GR relationship. You know. Okay, and also they have given the what are the magnitudes. The magnitudes is given because you will use them in your attenuation equation. And then distance is also given, which also you will use in your attenuation relation. So then find the probability exceeding a PGA of 0.3 g at the site in 100 years using the probabilistic approach. Okay, and considering a lower threshold, that is also given, that is m naught. So you need to get the lambda m naught, this quantity you need to get. So you need to be specified with this m0 or m naught, that is also given. Everything is given. So it looks very lengthy, but it is lengthy because it is trying to give you each and every input you need to use all the equations. That's it. Now assume an average shear wave velocity of this. That is again, whenever you will find anything physics related thing, be sure that you have to use them in the attenuation model. So this is again for the attenuation model. For the soil deposit at the site, assume also that the closest distance to faults correspond to their geometric center. So now these are, everything is defined so that you can solve it. That is the only thing. So and solving is very easy. Equating the I mean, from that equation you can get lambda m0. As I said, it is in terms of alpha and beta. AB values are given, so use this thing, that constant log 10 to the base e 3.30, whatever you use them, you get this thing values. I think it's a mistake, it is 2 point something. It is log 10 to the base e. I just copied from the book this part, so there is a printing mistake anyway. So you will get this values. So you will get lambda 0. Okay, the lambda 0, you store them. You need where, after getting your probability of exceeding the hazard value y greater than small y, you need to get your lambda iy, right? If you remember, for that you need these two values, so you store it somewhere. Now we are into the actual problem, that is we need to now solve this triple integral. This quantity we are now going to solve. One, you will solve this, you will multiply with this lambda m0 to get your lambda iy. Then your last stage, just put into the Poisson model to get the hazard. So now what you are doing, this is the attenuation model. Is the same attenuation model that I have shown. They have used this thing, so for which all parameters are given in the problem. You directly get the values from the table, from the coefficients, and then you get your sigma for that, so that you can construct your z. How to construct z? I have said now this one. This what you are now doing actually with all the specific cases for this problem. This is your attenuation model is this by this. I'm not reading out. You can get this thing from the slides. So you will get this. Z value here. So this is the Z. So now this is the integration. Okay, where this thing is getting used? It is getting used after you evaluate the first integral. It is function of Z. S is dummy variable. You do this integration first, keeping dm and dr, m and r as constant for the time being. Then that function of Z, whatever you will get, you put this thing here. Now you will get double folded integration everywhere r and m there. So then you integrate with respect to anything, whether r or m. Order is not, order doesn't matter. You know, this is a property of integration. But whenever you are integrating with one particular parameter, you are treating rest of them are constant for the time being. So then you do m. So then m will get marginalized, and then finally you get r. So after that, none of them will become property of m, r, or z, because all are different integral. So then finally you are getting some number, and you will get this number. If you, this is not so easy, it will take a lot of time. But these days, you know, you need to do all these things with some computer program. You can use numerical integration techniques, so you really don't need to, you know, master all these, you know, formula of integration and all. You can always do this thing quite comfortably in your through numerical methods. So you will get this number. This is for your fault 1. And for fault 2, you have, you know, different values of your b values, right? So these constants are different. So no matter, again, for the second one, same thing, you get this thing. So what you will get what is the probability that 0.3 g will get exceeded, okay, at your site from your first source. This is the same thing from your second source. Now you cannot add that way these probabilities. What you can add always the rate. So what is the rate? That rate of exceeding that particular y. So this suffix y means what is the rate of that particular hazard value getting exceeded per year. So then that whatever the corresponding lambda 0, the lambda 0 is coming from GR relationships A and B value. So you take A and B value for your first source, and you got already your P of this thing for your first source 0.015, whatever it is, this one, right? So first source, and then you will get the number, the rate, this many events per year from source 1, again this many year from source 2, and now from the equation, from equation 15 I have shown earlier, you just add them up, the number of rates, because it's the number of events you can always add. Okay, it's very simple, very basic thing. I mean, there is no problem, no proof, nothing is needed. So many events are occurring from various sources. You have to add them up. You are adding up, you are getting this number. So now you know everything, because this is the very first problem where this thing was given. The second problem, it was given directly. Now you had to take all the pain to get this number in real life condition. So what you are now getting as a result, and according to equation 9, which is nothing but that 1 minus, you know, e to the power minus lambda t, the probability of exceedance in 100 years. So that is how your now design life is coming into the picture, okay, or the exposure period of peak ground acceleration of this much g. Site is this. So now you can get 0.30 g, right? What is the probability that this will exceed, right? And look, the difference, 100 is there. So you are now you have taken into account the exposure period. That is the actual hazard we are interested in earlier there was no exposure period because it is given something has happened, what is the probability of that thing being exceeded. But now you're really taking into account the occurrence, that how frequently that event will occur. Then only you will get the complete answer, knowing the exposure time, that how much time you are waiting. That is also very important, that how much hazard you are expecting. Again, you think that you are standing in a risky zone, right? Let's say in a jungle, more time you will spend inside, it is more hazardous for you, right? So now you are getting the actual answer. If your design life is 100 years, it is this much of hazard. That means chance of this particular value being exceeded for a structure who is sitting there for 100 years is 0.062. So it is only 6.2%. Needlessly, if you reduce this thing, this number will also reduce. If you increase this number will also increase. But now I think you have a fair idea about how to, you know, from a very practical problem. You see this kind of problem, a very practical problem statement. This is very much, you know, handy. You can have situations, you can have a region for which getting information at this level is not very challenging. So you have hopefully now everything with you to do the seismic hazard assessment. Now, if you want to do this, now you can have some natural extension. What are the natural extension? If you want to get a kind of hazard curve that I have discussed earlier, you can do that. How? You keep on varying this value, right? You start from small g to high value of g. Similarly, it will change. It will change from 1 to 0. If it is too small, you will get this thing 1. That means a very small g, let's 0.0001 g in 100 years, chance of getting that thing exceeded given the background seismicity is 1. It is bound to exceed that value. Similarly, if you have a very high value of g, let's say there is a threshold, let's say zero point 0.7, you found this is 1. Sorry, this is 0. That means anything greater than 0.7 will be 0. So there is no chance, or actually you will not get no chance because it's exponential, but the chance is maybe less than 10 to the power minus 4 that this will getting exceeded. So that means that value is really very unrealistic. I mean, sorry, it is very much unrealistically high. So you will never experience this thing in that particular region for a period of 100 years. So then you can also get a kind of hazard curve for that as well. Okay, so I think that's enough as a first lecture or a kind of uh, I mean, through presentation whatever idea you can get about seismic hazard. I think it is quite okay with you. Now I am open for any kind of questions related to this thing if you have. Okay, okay, Vipin, you can now take over. Yes. Okay, chat box. Okay, chat box. Yeah. Um, okay. It is mostly the good afternoon message. Yeah, but I think it is more efficient, one by one, if they ask something rather than all of them. There is no raising hand kind of option here, so that you can figure out who wants to say something. Okay. But anyway, there is a general kind of thing from my side. Okay, even if you don't have any question and you have some kind of question later on, you please don't you rather encourage them to write you the questions. Okay, you can then find out what are the independent questions, send it to me. Okay, I will send reply to you, no problem at all. Okay, it doesn't end here. Okay, uh, I have delivered, so I want them to understand. Okay, that is my first job. So if for whatever reason they want to revert back later, they can ask you send me the questions, I will try to answer. Okay, no problem. Yeah. Yes. Oh, wait. See, this is very much debatable. See, debatable in the sense it depends not only on the distance itself, but also the size and also the distance. I mean, how far you are from the site, I'm trying to say. See, you have a size effect, right? Now, if you are closer, very much close to the site, okay, and if the event is quite big, now if a bigger event means you have a bigger rupture zone, right? So now if you're really close to this thing, the source is really not a point. You can really see a big area contributing to the tremor, right? So in such cases, some distance which will take into account the size of the energy release is very important. So there your hypocentral distance, epicentral distance may not work well. But on the other hand, let's say you are quite far away from the site, okay, and your earthquake size is also smaller. That means physically you will see the source as a point, right? So then any point in the source for that matter is going to serve the same purpose almost. So in that situation, you can assume that okay, I will go by the hypocentral distance. It is fine. So it is more like what? So let's say you have identified a big crowd. Okay, noisy crowd far away from you. Okay, and then the entire crowd will look as a point from you, right? So if you proceed towards the crowd, you will see that the sound is increasing exponentially, following the inverse law, square law, roughly. Now, if you are getting too close to the crowd, you will see that the sound will saturate, because then you cannot hear the sound from a person who is far away from the other side of the crowd. You are only listening to the individuals who are close to you, right? So in that case, that epicentral distance or point source somewhere within the crowd is not going to work. Okay, so it is just like that. It is highly subjective. It is debatable, but usually that is the reason we are doing some mix. That means epicentral distance, and then club with some kind of size of the source together, like epicentral distance plus, let's say, some measure of the source dimension square root of this and that. So some kind of distance metric, which is not going to become zero, even if you are either sitting exactly on the epicenter or your site is exactly at the hypocenter. Your distance metric should not become zero. So in some way it is a mixture of these things. So it is very much complex. Even I don't know this thing much. Various seismologists are working in this area itself, that what is the best distance. But for all practical purpose, especially when we are little bit of far side, more than 30 kilometers away, 40 kilometers away from the positive fault, it doesn't really make a very big difference, because the sigma of that attenuation model, that we're talking about, it is so large that it will basically normalize everything in some sense. Okay, so when you are really going for a hazard level which is really stringent, let's say exceedance probability is only 1% or only 2%, then this kind of thing is not going to matter much. And anyway, sometimes we use logic tree that I didn't want to cover here. So the main idea that you will not follow one particular model, one particular thing. You will follow various things, and you assign different weight for that. So one particular approach I will assign. Let's say if I use four particular approaches, using even maybe your attenuation model is different. What you have said, hypocentral distance. Somebody can say no, I will use distance from the fault rupture. Okay, fine, you take it. So this is how we can take 4 5 things. Individual estimates are there, and I will put different weight. So fair enough will be, I have four such methods, every method will have 0.25 weight. So then my final probability estimate will be uh, weighted sum of all of them. Okay, so this is how you can actually get rid of or to minimize any kind of subjectivity involved inside. Okay, this is a good question. This is subjective, so we have to, nullify the subjectivity only through this kind of logic tree approach, where we have multiple kind of analysis and assign different weights for that. That's, yes. Yes, I see. If you want to do a test study for that, practically, theoretically, there is no issue. But the practical problem is this. I mean, you must get a complete, that I say, no, there is a kind of, quantities estimation that will tell you whether your data is complete or not. So unless until you get a complete catalog for every magnitude range, because you see, when you are using your GR relationship, it is magnitude exceeding certain value, right? So for such every class of magnitudes, your catalog should be complete. Now that complete catalog, if the number of year of completeness is not very long, then you will not get a stable estimate. Okay, because once you are talking about the average annual rate, so you must have at least a few good numbers of annual rates over several years. Then only your estimate will be stable. So then, even though you can do, whether how much quantitatively sound that thing will depend on the earthquake catalog. Now, if your region is not seismically active, then what you will find, that most of the catalog data will be far away from the place. Okay, so that means when you are going to use this distance in your attenuation model and all these things, the majority it will be a far side event. So your hazard there will not be very high. That is not a problem. But what I'm trying to say, that in general we don't consider a radius more than, let's say, 250, 300, or at the most 400 kilometers from the site. Okay, no matter whatever be the earthquake magnitude, I mean, assuming that it will be not exceeding 7.5 at most, it maybe. If it is happening, say, far away from 400 kilometers, then as per the attenuation law, you will find that the whatever ground motion shaking you will feel at the side is not going to pose any threat. So, if your site is really seismically very much less active, and you will not find a good number of causative events statistically based on your historical data, not within 400 kilometers, then you are not going to get any, I mean, proper, this hazard estimation, because somewhere we need some numbers to get some stable estimate. Okay, and also getting attenuation model also region specific is tough, because unless until you have records in and around your site, you don't know what is the path propagation effect, right? So then you have to really find out some attenuation model which is very sophisticated, where the geology of the wave propagation is also accounted for. Now, the next challenge is that even though that is accounted for in the model, you have to give this data for your region. Now, how do you assess all those sophisticated, information, divulge this information for your region is also difficult. So that is the reason these kind of studies are more, favorable for a region which is seismically very much active, because getting data and having region specific, attenuation model or AB values are easier. But still we do because we borrow then seismic attenuation model and other things from other regions sometimes, which are, applying some judgment. You can say that okay, it is applicable for this, and then you have such multiple possibilities. You use your logic tree approach, right? But AB values you have to find out for your region. That is not a problem, because usually in India, everywhere you find some earthquakes from our catalog data. You can find out always some good number of earthquakes. But the attenuation model, I'm pretty sure that if your region is not seismically active, then getting an attenuation model developed specifically for that region is near impossible. So then you have to find out some attenuation model developed for a region where the seismicity is comparable, or your ground, your geology, etc., are comparable, and accordingly you have to decide. Yes, yes, it is possible. Of course, it is possible. Mm, mm. You can do deterministic in the sense, because see, one data you cannot use probabilistic. So you can then say that okay, if that earthquake occurs exactly at that position, right? What is the hazard associated with that? I mean, that kind of thing you can try with the recurrence rate is there, and then you have a regression model borrowed from somewhere. You can do that, but getting your AB values within a region of 300 kilometers, if there is no event, then it is very difficult to get those recurrence relationship, because stable estimate needs completeness and also good number. Otherwise, it is very difficult to fit any, straight line or any line for that matter, right? Some stability, some minimum number is needed. Otherwise, your estimate will be very much different. One new event can completely change your estimate. That thing should not ideally happen, right? Your seismicity model cannot change if one or two new events are coming. If your data is very high already stable, so one or two events will always be accommodated within the same framework and without much disturbance to the already estimated parameters. Okay. That is also there. Somebody can also take the azimuthal dependence, or whether it is fault normal or fault parallel. All these things are there. Some of the attenuation models where people are considering this. There are some attenuation models where people don't consider. It is completely their discretion. But what I try to focus on today is the essential components. So every component, while there is scope of improvement, there is scope of generality. I can use a much more sophisticated attenuation model. But essentially, the purpose is the same. They will give me what is the probability that a particular level of intensity measure will get exceeded given the magnitude and distance. That statement is not going to change. Okay, only thing is that the estimate will become richer. Estimate may be better if my attenuation model is more sophisticated, taking into account multiple factors. Okay, so that list of factors that I have said is not exhaustive. Okay, there can be n. Ah, oh, both the it is not given. I just copied from the figure. Maybe mm, that I don't know. I have to look at that. I know that place. There may be some difficulty with getting this the intercept. It is basically the intercept, right? So I don't know. That I have to see. I will find the reason. Okay. Effect of yes. So again see what okay. Again, it is the part of the physics. It will come into the attenuation law. Now, what I'm shown the attenuation equation. If you see, can I share the slide again? It is I think better if I share the slide again. So just a minute. So okay, you are presenting. Okay, I'm presenting. But why the is it already shared? It is shared, right? Okay. Now. Now you see, this soil is there in the attenuation model itself. Okay, so that is a crude thing. Okay, so you can separate this thing into two parts. In one part, you will find an attenuation model that will give you the shaking at the bedrock. Okay, in next stage, considering whatever your soil layer is there, you do a rigorous analysis of soil propagation through some software like Shake or maybe using Plaxis, whatever some other find relevant software. Using that, you can always estimate what is the intensity of, like, I don't know the softwares though, but I think there are certain softwares which can give you some kind of better calculation. Some kind of physics is now involved that how a wave will propagate to the soil, right? So if you can address this thing, then the effect of soil layer is taken into account. So it is not going outside the framework. So today I was trying to tell you a framework. That framework is a layout that is applicable every time. But the inner modules can always be made more sophisticated. So here in this attenuation law, there are some attenuation law we don't have the soil part. So don't take the soil part because it takes into account the soil in a very crude way. There is no, possibility maybe to input that you have multiple layers of soils, right? The question is very much valid. If you have multiple layers, stratifications, then you have different kind of, the way the propagation dynamics will change. So if you really want to account for that more accurately than this attenuation relation could do, then you have to go for some attenuation model which will give you the estimate at the bedrock, and then you on top of that you model the soil. You can find out a better site amplification analysis considering the stratification of the soil. It is possible, and then finally you will get this estimate, and then you put it into your probabilistic framework. No problem. Are you getting my point? Yes. Okay, fine. Welcome. And as I have said, you please, receive the further queries. Okay, no problem. And then one time, maybe after a week, you just send me all of them. Okay, removing the repetitions, and I will take out some time. It may take some time, but I will get back to you with answers to all the questions. Okay, 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 bye. Okay, 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 okay. Bye, everybody.